Hi everyone. I want to go over a new feature that I put into the PCB Toolkit version 8.32. I'm running version 8.33 for the purposes of this demonstration, but it is functionally the same program. There was just an issue with the help file that I had to fix in 8.33. This one is called load current. It's part of the conductor's property tab. It comes from a user suggestion, which I thought was a good idea, so I put it in. I want to be clear though, because it's a little confusing. The load current here, loaded voltage drop, and the loaded conductor temperature, those three things work together completely separately from the rest of the calculator. That's why it might be a little confusing. I didn't have time to put an entirely new tab in there for just this function, so I added it to the existing conductor property. So I wanted to clarify this. So the calculator works just like it always has. You put in a conductor width, it solves a conductor current based on your given temperature rise. So a 50 mil conductor, 50 mil wide conductor, 2.1 mils thick will what it solves is a conductor current of 3.7232 amps flowing through that geometry will raise its temperature by 20 degrees C. So this geometry finds a DC conductor resistance like it always has, then it finds a voltage drop. If you take the DC conductor resistance that it found, 0.00768 ohms, and I multiply that by the conductor current that it found, you get 0.2859 to 0.286 volts dropped across that conductor that happens to be 1 inch long. The load current is separate in that it takes, what it does is it finds a loaded voltage drop at a loaded conductor temperature. So it takes that 1 inch long trace of 50 mils wide of 2.1 mils thick, it uses the conductor DC resistance that it found based on that geometry, and it multiplies it by a separate current, a load current, a user input that is separate from the solved conductor current. So I multiply that times 5, and I get 0.384 volts. So that means for this geometry, you put 5 amps through it, you will get 0.0384 volts across that 1 inch trace. The loaded conductor temperature is down below. It says that 5 amps through that geometry, the total temperature of that trace is 138 degrees Fahrenheit. Excuse me, I've done this on the bench where I've taken boards with known conductor widths. I've run current through them using load resistors to try to come up with exact currents. And I've used a thermal imaging camera. And I find that traces 50 mils and wider, it's pretty accurate. Things below 50 mils, it starts to get a little squiggly. That's just the nature of the IPC formula. For example, if I put in a 10 mil conductor width, the temperature goes up to 728. If I put in a 5 mil, it's 2,000 degrees. So we'll go back to 50 here. I wanted to show you this. I know that the formula works. It's the same formula. What I've done is I've taken it and put it into a separate subroutine and just algebraically shifted things around to solve for the loaded conductor temperature. I know that it's accurate, so if I take the 3.7232 amps that it solved, put it in here, and you'll see I get the exact same temperatures, which is these two temperatures added together gives me conductor temperature. I'll switch it over to metric here. It'll be a little bit easier. 20 degree temp rise, 20 degree ambient gives me a 40 degree loaded temperature conductor. There is a little bit of a rounding issue with the formula, but it is what it is. Let's see if I put it in here. if I put the exact same number in there, I should get exactly the same numbers. There we go. Like I said, it's a little confusing, so I wanted to make a video explaining some of this. If I put in, for example, not 50, that's a bit big. Put in 10 amps. This geometry will give me a 408 degree temperature rise, which is pretty hot. Loaded voltage of that, so maybe you want to, you know, make a little bit wider trace there to lower that temperature down. So I hope you like it. Comment below on what you think.